to all of you. Alright, I'm Shikin Aziz. So today my lecture material content will be on thin wall vessels under internal pressure. Whereas this is another topic in EPF 4801 process equipment design. Alright, for my undergraduate student. Alright, so the main reference for this lecture material are taken from chemical engineering design. Alright, textbook, okay, whereas the author is Towler and Synod. All right, so for designing vessels, okay, for designing a vessels, it is important for us to determine the wall thickness because the wall we must make sure that we calculate sufficient we can identify sufficient wall thickness to support, okay, and to maintain the shape of the vessels. All right, and all right, so basically the vessel the thickness of the vessel that we determine should able to withstand with the internal pressure or any stresses, okay, that may arise due to other loads, all right, such as fitting or due to the any attachment, all right, on the walls of the vessels, right. So for a cylindrical shells, the stresses in the walls can be determined from simple forces balance. All right, so because as I said, in order for you to calculate the wall thickness, you need to identify the stress, okay, the acting on the wall. So and then the wall stresses must balance with the force, okay, the forces due to the pressure that acting on the wall. So talking about this, okay, they are basically the direction of the the direction of the forces, they are two. All right, let me show you, okay. So but before that, I want to show you this equation first. All right, this equation, okay, these two equation is basically the equation, okay, that's specified by ASME BPV code, okay, under section 8 division 1. All right, so this is for hoop stress and this is for longitudinal stress. All right, I would like to show you just a very quick how to derive this equation, okay, but of the equation that I will get is slightly different than the one that I showed on the slide. Right, I need to minimize this and then I need to open my whiteboard. Okay, class. So for stress, okay, so the direction of the forces and stress, okay, can be illustrated by this drawing. Let's say this is the part of the body of the vessel and the vessel's shape is cylindrical. Okay, and then we do have, okay, this, okay, the cross section, and then I'm using the right pen here to show the stress direction. Okay, so you can see that this is a stress from the cross section but at the circumferential direction. All right, and then we do also have stress at this part, which is actually acting longitudinal of the vessels part. Okay, so this we call longitudinal. Okay, longitudinal stress. And while for this we call circumferential. Okay, circumferential stress. And then we also have a pressure that might acting internally of the vessel, all right, or outside of the vessel. But now we look at internal, okay, internal of the vessel. All right. So this is a direction of the stress and forces. All right. So now let's look on the equation that I'm going to derive. All right. So the force, okay, we consider the horizontal section, okay, through the vessels. Okay, because my direction of the drawing is a bit different than the textbook. All right. So we refer on the horizontal, okay, horizontal, but in this drawing it shows slightly different. Okay, now, okay, let's look on the longitudinal. Okay, I'm just using longitudinal. Okay, longitudinal, okay, force, okay. So the force for longitudinal, all right, FL, okay, I'm using FL for longitudinal, okay, can be derived as internal pressure times by pi, and then the mean diameter by 4. So this is mean diameter. All right, this internal pressure by. All right. Well, as stated in the books, that the forces that acting on the wall must be equally to the stresses acting inside the wall. So this force can also be derived, can also be expressed as sigma L times by pi and mean diameter and the thickness. Right. This sigma L, okay, this sigma L is actually a longitudinal stress. Okay, longitudinal stress. All right. And then this circumferential stress is denoted by H. Okay, circumferential H. Okay, circumferential stress is also known as hoop. Okay, that's why it denoted by H. Okay, sigma H. All right. So as this need to be balanced, so we can equate this equation pi internal pressure for equates with this equation, and then we can simplify the equation, and then we can get and simplify it. Oh, sorry, this one. Okay, so then what we get is internal pressure T by 4T. Okay, this is what we get. Okay, and then for alright, for force acting at the circumferential, okay, this can denote by can be expressed by Fv equal to internal pressure and this, and then while for stress that force, okay, by circumferential stress, okay, or hoop stress, we can also define it by using this expression. All right. Okay. Then both of these again equates because it must be balanced. So this can be write as this. Alright, and then we can simplify this equation. Okay, we can simplify this equation and rearrange it to get circumferential stress or hoop stress. Alright. Okay, then we can simplify. Do we need to can we simplify? Alright, then we can get internal pressure diameter divided by 2t. Okay, right, this is what we get. Okay, so now we need to identify the wall thickness. Okay, this is how we can find the wall thickness from this equation. But in order to get the wall thickness, okay, the diameter here can be substituted by this internal diameter plus by the wall thickness. Okay, all right, and then the value for the stress here, symbol for the stress here, we can represent by using symbol of S. Okay, where S is actually a maximum allowable stress. Okay, as maximum allowable stress. So let's say for this, we substitute S and the value for this. Alright, we will get we can get S equal to pi internal pressure, and then di plus T, and then Wt, and then this we rearrange it and we can get T 2S minus Pi. Alright, so this is what we can get when we derive it from the expression for thin wall thickness. Okay, thin wall vessel. Okay, but the expression that shows here, okay, the expression that's been shown in this slide, okay, this is basically been derived from a thick wall vessel. Okay, it's slightly different. Okay, why is slightly different is due to this. Okay, is due to the is due to this value. Alright, and then another thing, we can also add up this E. Okay, again similar to okay, this the maximum allowable stress here. Okay, sorry, the previous video was stopped. I don't know for some reason. Alright, it stopped at that point, and now we continue with the next section. Alright, so you can see that. Okay, please don't feel that it's a bit weird because previously I'm wearing a different color of scarf. Now it's different scarf colors. Alright. So that is the challenges that I have to face with this distance learning. Okay, so from previous the section of this video, all right, I stopped at about to explain on welded joint efficiency. So right, so welded joint efficiency is actually uh, been used in order to show the strengths. Okay, the strength. So there is a possibility that when there is a welded material, it could be the strength it will not be similar to the original plate or virgin plate. All right. Okay. So, but the way it been how to say substitute inside the equation is not is a bit different. Okay, where it's only multiplied uh, by the multiplied to the maximum allowable stress. So here, okay, let me show you to this equations. So for this one, oh sorry, okay, all right. So by insert the welded joint efficiency, all right. So it's basically just multiply the welded joint efficiency to a maximum allowable stress here. All right, do this. All right. So the S multiplied by E is actually to show the possible uh, lower strengths. All right, lower strengths of a welded joint. All right. So we only multiply with the S, okay, not with the other term inside the equation, okay. All right. So this E, okay, you need to know that the welded joint efficiency, when it is 1, that's mean uh the strength is the same as the virgin plate or original plate. All right, so been welded. Okay, but if E less than 1, so that's mean the welded joint, uh, the strength of the welded joint is reduced compared to, okay, or is lower, slightly is lower compared to the virgin plate. Okay, all right. So 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 that's why for the final equation, all right. So the final equation, oops, sorry for this. Okay, for the final equation, there is a E, okay, the symbol for welded joint efficiency. All right. Okay, so this is basically the one that I have shown to you. I have shown to you on the whiteboard just now. My electronic whiteboard is a little bit different. Okay, because of this value here. All right, there is another constant here. So, but this is a equation. Okay, from the standard. Okay, you can use this. Okay, I recommend you to use the equation from the standard. All right. Okay. Then for on, okay. Well, this is for cylindrical shell. Okay. So basically, based on the ASME BPV code, it specifies that the minimum thickness, okay, shall be greater. Okay, if let's say you do for the hoop stress, you get two minimum thickness. Okay, you have hoop stress and longitudinal stress. So basically, the minimum thickness shall be the greater value. Okay, shall be the greater value determined from this equation. Okay, from this equation. So you need to select which one is the greater. If let's say from your calculation you get longitudinal stress, the value is bigger than the value for the hoop stress, so you select for the longitudinal stress, right? Okay. Okay. Then for spherical shell, okay, as ASME BPV code specify this equation to be used for spherical shell. So there are two different equations. All right. So basically, all this equation that I have shown to you. Okay, you can use any consistent unit. There is no limitation for using this equation. Okay. Alright, I stop here for the minimum wall thickness for the spherical shell and cylindrical shell. We shall meet again for the next video in another topic. Okay, alright. So see you in the next topic. Okay, keep safe, stay safe. Okay, see you again. Assalamualaikum and a very good day. Bye.